So earlier I told you that the default change detection strategy looks at all the binding expressions in a component's template, looks at all the properties used there, keeps their old value, and compares them with the new value when change detection is triggered. Now in this lecture, I want to give you a deeper understanding of why the default change detection strategy is implemented this way. So in app component, I'm going to implement a very simple change detector. You don't have to code along, just watch what I'm doing. So I'm going to declare a class. Let's call this change detector. Now here we add a constructor and give it an input, which is the initial state of the component this change detector is made for. So let's declare a private field here and call it old state. And initially we set old state to this input here. We also need a method here like isStateChanged, and we give it a new input. Now here we need to compare the value of this new input with the old state. If they are different, that means the state is changed. So, like this. Again, this is a very simplified implementation. Now, let's go in app component. Here in the constructor, first I'm going to instantiate this change detector. So, new change detector. Now, we need to give it the initial state. So let's declare input and set it to Apple. And then we can pass it here. All right, now let's simulate a state change in the application. Like somewhere the user is clicking a button and we're modifying this input. Now, you know that this input is a string, which is a value type, so it's immutable. So if I want to call to uppercase on this method, I need to get what is returned here and reset the input because the original input is not modified. So this simulates a state change. And now let's imagine change detection runs. So we're going to call cd that is state changed and give it this input. And then we can log it on the console. What do you expect to see in the console? Well, let's have a look. So we get true. The reason for that is because our input here is a value type, and now we have two different variables in memory with two different values. One is the lowercase apple, one is the uppercase apple. Two different variables with different values. However, if I change this input from a string to an object with the title property set to Apple, and then modify this line to update the title property, what do you think we're going to get in the console? Let's have a look. We get false. Isn't that interesting? We have modified the state, but we're getting false in the console. The reason for that is because our input is a reference type. So the reference has not changed. It's still the same. And in the implementation of isStateChanged, look, we're comparing the old state with the input passed to this method. These two objects are the same. They have the same reference. In other words, old state and input are both pointing to the same object. So for this reason, the default change detection mechanism cannot rely on the inputs passed to a component. Because if the input is a reference type, simply comparing the references does not tell the change detector if there are any state changes or not. So it needs to look deeper. That's why it needs to look at every binding expression in the components template. It needs to look at all the properties used there, keep their old value, and compare them with a new value. Now, earlier I told you that if you're working with complex components with large data sets, all these comparison checks may have a negative impact on the performance of your application. It's not a rule. It really depends what you're building. So you need to do profiling, as I will show you later in this section. So if your profiling shows that yes, all these extra checks are having a negative impact on the performance of your application, then you can use on-push strategy to reduce the number of comparison checks. And that's what I'm going to show you in the next lecture.